Okay. All right. So let me switch over to the book here. All right. So say that again. What number?
Question 10, chapter 28.
Okay, number 10. All right. Let me scroll up here. So 10 says, oh, using only 3 resistors. Okay. Find 17 resistance values that may be obtained by various combinations of one or more resistors. Okay. Okay.
So does that mean we just make like random circuits and we can use like the 2 ohm and 4 ohm resistor, or like just use them randomly, or do we have to use them every single time?
I think randomly, if you're going to get 17 out of them, for example, I think this is what they're after. I think I'm just going to start counting. If I did just one by itself, I would have, a 1 by itself, a 3 by itself, and a 4 by itself. So that's 3 of them.
Mm-hmm.
Okay. Then if I would put 2 of them together, I could hook them, let's see, in series or in parallel. So I can do the 2 and the 3, but I also could do the 2 and the 4, and I also could do the 3 and the 4. So that would be 6 more. So that's a total of 9 combinations. Now, here's where it gets kind of interesting. If I were to do all 3 of them, let's see, all 3 of them could be, and I'm going to have to do some drawings here, in series. Okay.
So we're at,
and they could,
at 10 if you do that.
Yeah, then they could all be in parallel.
So that's 11.
Okay, so 10, 11. Okay. Then I could do something like this. I could have the one in just, I'll call it in series with a group of 2 of them that are in parallel.
Okay.
And then I would have, let's see, how many different, so at the one in the series could be the resistor of 2 ohms, of 3 ohms, or 4 ohms. So that'd be 12, 13, and 14.
So it's basically just saying make 17 different combinations.
Okay. Yeah, that's what I'm getting out of it.
Okay, cool. That makes sense.
Okay, and then okay, I'm glad it makes sense. And then there's 3 more. I'll let you think about those. But yeah.
Okay, yeah, I just wasn't sure if I was supposed to use like all 3 of the resistors at the same time and get 17, or if I could mix and match different resistors. But that makes sense. Okay, cool.
Well, and I'll just say it out loud, is the next grouping that comes to my mind is that 2 of them are in series, and then that resulting series is in parallel with a third one. And then that would give you 3 more.
Mm.
And I think that might do it. 14. Let's see, how many do I have? 14. So it'd be 15, 16, and 17. Yeah. So that's 17 of them. So they're just trying to get you to, I guess, be creative and realize that, a box of 3 resistors really can be arranged in a lot of combinations and give you a lot of different resistances.
That makes sense. And if Anthony has no questions, I have a couple questions on 17.
Okay, let's see. I'll go to chat.
Actually, I have a quick question.
Okay, go ahead, Anthony.
This is actually, I never got to ask you last week about chapter 27.
Okay.
Number 56.
Okay. Chapter 27. Did I hear you right? 56?
Yeah, 56. It's these these shape problems.
shape problems. Okay, I'm not
Different
sure.
shapes that have resistivities.
Oh, I think I know what you're talking about. Okay, hang on here. Let me activate my
Those were
camera.
actually the questions I had, so that works out. Awesome.
Oh, good. Good. All right, let me write that down, and I'll write down a timestamp. Let's see, what is it now? 12:39. I didn't write down when we started. It probably was about 12. I'm going to guess 32. Okay. Yeah, and so let me do a couple things here. Let me start by sharing my screen. So I got a camera rolling and connect the Bluetooth for this session. And then while that's making connection, let me jump over. There we go. Let me jump over to, all right. Oh, wait, don't want to do that. Okay, let's jump over to the textbook. All right. Okay, so when I need to go back. So you say chapter 27, and yeah, there's a couple of them like this. You say 56. Okay. And 56 has got this cone. I guess it's a cone with the tip cut off. Make it a little bigger so I can read it. It was 100%. Okay. And I'll get rid of this and kind of draw the cone. I think if it'll be okay with you, I'm going to draw it this way. I'm going to put the cone on its side. Not that it has to be in any way, but as you'll see, I think since the area is changing with the length, there's going to be some calculus involved and adding things up. So what I guess I want to first remind you of, I should write here in case anybody's scanning the video. So chapter 27, number 56, page 1. Is that we learned back in this chapter that the resistance of a material was caused by 4 factors. 3 of them show up in this equation, and that's the resistivity. In other words, what kind of material is it? How long is the material? And what's the cross-section area? Okay. I say 4 because then the resistivity changes with temperature, and that's not so obvious when you look at that equation. But those are the 4 factors that affect the resistance. And so here's how I want to think about this. Since it has to do with the area, and this area keeps changing, let's think of this cone as a slice or a bunch of slices. And so little coin-shaped objects. So kind of if you imagine stacking a bunch of discs, that over here the discs have a big diameter, and over here they have a small diameter. In fact, they even label it there in the diagram that it starts with a small radius of A, and by the time it transitions a length of H, or height of H, depending on how you hold it, it has now increased to a diameter of B. And so maybe, a visual picture might be something like this. On this end, you have the biggest coin, like a quarter. And then you go down in size, quarter, nickel, penny, dime, okay? And so you got this cone shape. But what I could do then is say that the total resistance is the resistance going through the first coin plus the resistance going through the second coin plus the third coin plus the fourth plus the fifth, blah, blah, blah. Okay. And so I can imagine these coins being infinitely thin. And so they each have a resistance of dr, and I'm going to add them all together to get the total resistance. So that's probably the first big step, is to realize that I can treat this not as one big object, but as a summation of a bunch of little objects, a bunch of little coins. And by using my calculus, then I can add them up. And the reason, of course, that's helpful is because then when you put in the equation for the resistance of a coin, coming back up here to this equation, you would put in, okay, what's the material? What is the length of it? Now, since the current is going through this way, we would call this maybe a dx. And that's why I laid it on its side, because I thought you might appreciate the calculus with a dx a little bit more than a dy, not that that was much of a change. But so that would be the length of my coin, and then I would have this area. And of course, that's why I needed to switch it into some calculus, because this area then changes as you move to different points on the X grid, if you will. In fact, if I kind of put a grid on here, maybe I'll put the origin right here. And so going in this direction is the x-axis. And then, of course, you might label this as the y-axis. And now, as I continue on here with my calculus, I'll realize that if anything changes with x, I have to write it as a function of x. And that's where this whole thing about the area comes in. Because I know the area of one of these disks would be pi r squared, where r is the radius. And so again, we would start with a small radius of A and continue on and have it keep getting bigger until we got to radius B. So the radius is changing. And so maybe I'll just take advantage of the fact that the material stays the same. And of course, pi is a constant. And so these numbers can be pulled in front of the integral. And so I got that. And so I'd say that's probably the first one.
How come you didn't pull the r out?
It's not a constant. R is the radius of each disk.
Oh, I see. Okay.
Yeah.
So are you going to integrate in terms of x or in terms of r?
Well, I have to do x. So yeah, I still got some work to do.
Okay.
So like all of these, you I think what can be a challenge for this class is that you guys learn to do a bunch of calculus, but you always, in your calculus class, you always started with a calculus problem. Physics is not like that. Physics is the applied of the calculus. So you have to start off thinking about the problem and see how it leads to a calculus. And then, of course, then get to a place where you can actually do some calculus. And I think that's what you're asking. You have to have these written in terms of x before you can actually do them. Mm-hmm. And so that's where what is kind of the difference between learning math in a math class and applying math in a physics or engineering class. Okay, so you're pointing out something that hopefully is clear to anybody who's going to watch this later on, is that you can't really do this until you realize that r, the radius, is getting bigger as you move across, and so I need some kind of way of describing r in terms of x. And fortunately, here's where I can come back to my algebra. If I come back to this picture,
slope of a line, huh?
Yeah, see here, this, if I this would be the radius going up, and so that would be the y-axis. And so if I think of r as y, where y is mx plus b, now I should be careful with the b because there's a b in this problem, and that's not what I mean by b in here. What I mean by b in here is just from your math class, that this is the intercept. So maybe I shouldn't write it that way. That could be confusing. Maybe I should write it as slope times x plus y intercept. And so if I take a look of this thing, is this line going out is really the radius. That's why I'm going to set y equal to r. And the slope is the rise over the run. Okay, so if you go from here to here, the run is the h. So the rise, well, we get to b, but we started at a, so it would be b minus a. So there's the rise and there's the run. And then the intercepts, well, the intercept is back here where it crosses. That would be A. So I can now use that and say, okay, R total equals, and I have the row over the pi. And now I can write this as a, I'll leave the dx alone upstairs. But here's the big one. I get the b minus a over h times x plus a and quantity squared. So all of that right there is a mathematical function for the radius as I start with x equaling 0 and continuing on until x equals to h. So that's the big one. And now, of course, I would then start at x equaling 0 and go to h. And this now kind of turns into more of a math problem, but it's still not easy. But it looks, at least now it looks like something that you've been doing for a while and probably have more experience on it. So I'll just go page 2. To me, this is kind of screaming U sub. So I'll go U equals, and maybe I'll just take that whole thing downstairs, which is a B minus A H X plus A. So then I can go DU equals B minus A over H dx. So now that if I do my U sub, and this whole thing is U, so downstairs I just have U squared. And then of course upstairs I want to put in a dx. So rearranging this would put an h in the numerator and b minus a in the denominator and then a du. And then taking advantage of our integrals being linear functions, meaning we can take constants and pull them out in front. I just now have an integral of du over u squared. Which this is probably best written as an integral of u to the minus 2 over u. So that u sub turned it into just a simple power function. And power functions, when you integrate them, you add 1. So this, when you add it to the exponent, you become u to the minus 1. And then you divide by that new exponent. And maybe to simplify it a little bit, I'll move the negative up top and then the u downstairs. Okay. And then, of course, keep going with this. So here's the rho, the h, the pi, the b minus a. I'll even put the minus out here. But then I have this 1 over u. So going back to my u sub, this is a b minus a over an h times an x plus an a. And then, of course, now that I've switched it back to x's, I should put in my limits. And I think I mentioned this in a few other videos. I'll say it again. When I do a U sub, when I first setting up the physics, I got the limits of my integration from 0 to h, but that's in terms of x. So once you do a U sub, your limits change accordingly too. And you can calculate them and put them in your integral sign, but I never do because I'm only going to switch it back to x's eventually anyway. So I skip all that and go to here. But maybe if I did, I wouldn't have to go back to here. Maybe, and that'd probably actually be easier. But that's not my normal operation. So, but it looks like it would have been easier in this case. All right, so then continuing on, this would be minus rho h, this would be a pi, this would be a b minus 2. And so now I can put in my values. And so this would be 1 over. And if I put in an h for x, those would cancel. And so I would just have a b minus a plus a. And then minus, and so if I put in a 0, I would have 1 over a. Of course, this right here, this minus a and plus a would cancel. And so I'd have a minus rho, an h, a pi, a b minus a. And then it looks like I have a 1 over b minus a 1 over a. Maybe doing a couple of things. Maybe first with the negative sign, I'll distribute the negative. So that would put a negative in front of there and change that to a positive when I multiply that out. But also, when you have fractions, you need to get a common denominator. So multiply the two together is the common denominator. And to get this, you would have to multiply by an a, and to get this to the common denominator, you'd have to multiply by b. And of course, that is b minus a, which is the same as that. So those would cancel off. So you'd have rho, you'd have an h, and then you'd have a pi, and then I'll just put it in alphabetical order, a times b, because I think that's what they listed. Yeah. And so sure enough, to show that the resistance is, and that's the little formula.
Okay.
Oh, good. That helped.
Yeah, it did. The only part I had it all except
Oh, good.
the
Which part?
y equals mx plus b, getting the slope of the line
Okay.
to the integral.
Oh, good. Well, actually, that's a really good sign then, because that means you did all this stuff here, all the physics stuff of it, where you thought of it as a bunch of disks, and then they're in series,
Yeah.
so you got to do a resistance, which, in the limit, they got to be an integral, and then it's an area, and then you just kind of got stuck with, okay, how do I convert the r into a function of x?
Right.
Yeah. But you got the physics of it.
Mm-hmm.
Good.
All right, thanks.
Mm-hmm. Nice. All right. Well, for all you other ones in the room, let me just say if you got a question, maybe so I can keep track of who's asking what first, shoot them into the chat room. Other than that, nobody does. I'll just take whatever and whomever turns off their mic and shoots a question at me. Oh, hey, okay, Leo. All right, chapter 8, number 10. Ah, okay, this must be a 122. So chapter 8, number 10. Got 12:59. Write that down for my video. And actually, that problem sounds familiar. Let me look that one up. Somebody must have been asking me about that one earlier in the week. Let's see. I got to find the textbook. All right. Chapter 10. Let me scroll down. Oops, too far. Oh, I mean chapter 8. That's my problem. Number 10. Okay, so rotations. Good. And oh, I don't even need to do that. Let me just go back. I called up all the homework purposely for just this. All right, I'm just going to go to the PDF here. All right, and then scroll down. So I'll try this again here. Chapter 8, number 10. Oh, now, is there a 10 conceptual? There is. Is there a 10 in the exercises? Oh, no, there's not. Okay, so you must be talking about conceptual here, and it says a flywheel with a large rotational inertia is often attached to the drive shaft of automobile engines. What purpose does this serve? Okay, let's see if I'll try to draw a picture here on my screen. As I said, a flywheel, and I'll just kind of make a disc here. And so maybe the disc looks something like this. And of course, there's an axis, and maybe I'll make the shaft kind of go back here. And so if you have this flywheel, which is essentially just a heavy disc and it's spinning, maybe I'll put the spinning here, so omega. Its inertia, its rotational inertia, I, if it's very big, what does that mean? In other words, this is really a question about what does the moment of inertia or rotational inertia mean? Your book uses the word rotational inertia, which is a good physics word. Another name for that is the moment of inertia, which is a good mathematical word. Since we're not calculating anything here, let's just keep calling it rotational inertia. So this, I'll just abbreviate rotational inertia. This rotational inertia means how, it's a measurement of how easy or how hard is it to get it to rotate, or how easy or hard is it to get it to stop from rotating. And so when you build a car engine, what if I can fit it in my drawing here? No, I wish I would have made that out of pencil so I can erase it. But there's these pistons. Maybe I'll put the pistons as a side mount here, that are inside a cylinder wall that attach to this crankshaft. And here's where we burn the gasoline. And that's why there'll be like a little spark plug here. And so the spark plug ignites and it pushes this piston down, and that turns the crankshaft and also turns the flywheel. But why have that flywheel? Why have something with a lot of inertia? Because two reasons. Number one, when this first explodes, it has to go back and forth 4 times, in a 4-stroke engine, 4 times before this refills with gas and we burn it again. So once this thing starts spinning, we want to make sure that it keeps spinning so that it will keep moving all of the parts back to, and like I said, it's got to rotate around. This has to rotate twice, which will move this thing back and forth. Each rotation goes back and forth. So that's 2 strokes. And then another rotation is back and forth. We want this to be able to complete it. So by having a lot of inertia, it is hard to slow it down. So once we got it started, it is hard to slow it down. And so even though the gas has stopped burning, it's still got to continue for a while. So that's the idea of the big flywheel. It will keep it going all the way through the complete cycle, the complete 4 strokes. And it can get back to a location where we can give it more push again, more energy. It also works the other way around too, though. If you didn't have it when this ignited, this would push on this crankshaft and it would spin really quick because it didn't have this. And so this is hard to get going. So this keeps that effect down. In other words, without this flywheel, if I was drawing a graph of, say, the rotational speed with time, when the gas fired, it would go really fast, and then it would taper out. And the gas would fire really fast, and then it would taper out. And so your machine would be running fast, slow, fast, slow, fast, slow. But by putting a flywheel on there, by giving it a lot of inertia, you take away from this dramatic fast, and you also take away from the dramatic slow. And so a graph with a flywheel might look a little more like this, where it goes a little fast on down to a little slow, a little fast down to a little slow, and it more stabilizes it. So that's really it. It's a stabilizing effect. Let me switch back over to the chat in case you asked anything. Did that help, Leo?
Yeah, thank you.
Okay, good. Anything else?
I'm good for now.
Okay, great. I wonder if I should. I wonder how that works. Does it really pause it, or does it make 2 recordings? Well, I'm gonna go with the idea that it's
Splice it together if you pause it.
okay. I'm
Battery portion.
sorry, I hit the button right there. What was your little challenge?
This question has the dead battery. You're charging a dead battery.
Oh,
I don't know how to address that.
oh, okay. Well, yeah. The way you charge a dead battery is you just send the current opposite that it normally wants to do. So in other words, the chemicals in it, and I'll just pick the old-fashioned lead battery, the kind you'd find in a car. It's got lead and sulfuric acid, and so you would in its natural state, it wants to make a chemical reaction so that the lead becomes lead oxide and the sulfuric acid becomes water. But if you force electricity through the battery, so in other words, you would have to have another battery that's got a stronger voltage, and you kind of force it the other way, some chemicals, not all chemicals, but some chemicals undo themselves. And lead oxide, sulfuric acid, and water is one of those. So if you force electricity the other way, everything that's already turned into a lead oxide starts to undo itself and starts to become lead again. and then starts to change the water into a sulfuric acid. Without writing down all the chemical reaction, that's kind of the basic idea. Now, not all batteries do that. I think you know, probably the most common battery, non-rechargeable battery, are those alkali batteries. So those alkali batteries, their chemical reactions are great, but they're so permanent that if you just run electricity, through them, you can't recharge them. So, you go buy an alkali like a Duracell battery. When you're done with it, the only thing you can do is recycle it, and then the recycle center and the chemical engineers will process it and undo all those chemicals and make them good again. But they can't do it with an electrical process, or I should say electrical process alone. Whereas probably the most common rechargeable battery to you is like the one in your phone. You probably recharge that every night, and that's the lithium ions. They're our latest and greatest technology in terms of batteries. They're very light and very powerful, and when you run electricity through them in reverse, they undo themselves. And so when you run electricity through them, they gain energy, if you will. They become a lithium ion, and then during the reaction they come to be a lithium. And it's not pure lithium either. There's a little more going on. I don't recall. So there's a little difference between a lithium battery and a lithium ion battery. But I digress into more of a material science or a chemistry at that point. But that's why you plug in your phone at night. You put it on a little charger, and your lithium ion battery is probably about 3 volts. But you plug it into the USB on your computer, that's 5 volts, and so it just forces the electricity to run the opposite way. Anyways, I guess I'm just chit-chatting away. It's probably best to kind of show you. So chapter 28, number 24 is your question. And so if I grab the problem here, should I look on the problem sheet or the textbook? Maybe let's go to the textbook here. 28, I think I am. No, I'm in the chapter 27. Yeah, that was your last question there. All right, let me change back to the other chapter. Oh, made it small again. Let me go to 100%. Okay, let me scroll up to number 24. And so 24, yeah, it starts off, a dead battery is charged by connecting it to a live battery on another car with some jumper cables. Determine the current in the starter and in the dead battery. All right, so their little circuit here looks like this. They've got a 12 volts battery. That's the good battery. And of course, as hopefully you guys got out of the 2-meter potentiometer lab this week, is that the way we like to model batteries is you get a certain amount of voltage due to the chemical reaction. That's this. We call that the EMF. Mm-hmm. And then the whole construction of it, the fact that it has sulfuric acid and it has lead and lead oxide, is that now it's got to flow through that material. And so there is a internal resistance. You wouldn't purposely put a resistor there, but just the nature of these charges have to flow, make a resistance. And so when you're jump starting a car, what you do is you take the negative on the good battery and you hook it to the negative on the dead battery. Now, apparently this isn't completely dead. They're still saying that you have an EMF of 10 volts here, and you have a resistance of 1 ohm. And so in this case, probably what's happening is our concentration of sulfuric acid has dropped enough that we're not getting as much reaction here. And then, of course, given that there's less sulfuric acid, it's probably because we used up a lot of the sulfuric acid, and so a lot of the lead has become lead oxide and also water, both of which do not conduct as well as lead or sulfuric acid. So the internal resistance has gone up by a factor of 100. So when you take so this too is an internal resistance. And so what you've done is you've taken the positive side of one battery in the good battery, and put it on the positive side of the dead one, and the negative of the old one and the negative one there, okay? And if you just left it there, you would be, just essentially charging up that battery. However, if while you still have it hooked up, you turn the switch on to the starter motor, then that's what this resistor here is all about, is that, okay, now this electricity wants to flow through this starter. And this resistance tends to be really, really low. So instead of the current from the good battery going and charging up the old battery, at this moment, it probably instead is going through the charger, through the starter motor, and even some from the dead battery will be helping out. And so it'll be kind of interesting to see what's going through what, because it says here, determine the current in the starter and the dead battery. I'll just add to that. We might as well find the current also in the live battery. So let me draw my circuit like this. I'll say that the current is coming out of the good battery, call that number 1, and it goes along to here. This is the one that's kind of questionable. If the dead battery is really dead, then the good battery is going to have to continue to charge it and do the starter motor. That's not usually what happens. And given that we have 10 volts, I think that what's going to happen is the dead battery is going to contribute a little bit. It'll be interesting to see. Let me emphasize, though, I'm just going to label it that way. It purely is a guess, and my guess could be wrong. And when I work out the math, if this current number 2 is a negative, that means it's opposite of my guess. So don't spend too much time on a guess like this. What I do know for sure, though, is that the current, which I'll call number 3, goes across this to the starter motor, and so the current's going to go this way. So, and even then you could get it wrong, but this is such an obvious guess that I don't think there's any way I'm wrong. I mean, I give myself a 99.9999% probability that the current for number 3 is going to come out to be positive going this way, and also the current for the good battery is going to be going the way I picked, and so that'll be positive. One I'm not real confident with is whether I2 will be a positive or a negative. Like I said, it could be such that this voltage is so low that this battery at this time is doing, 2 things. It's actually charging the dead battery and starting the car. But like I said, at 10 volts, it's probably rough to know. And so that's why it's going to be fun to find out if I2 is a positive number or a negative number. All right. So like I was telling you guys before the break, and let me switch back to the Zoom on this screen here. I can see things a little bit better. All right. And you could look for equivalencies. Turns out with these batteries here, there is nothing in series and parallel, so we're not going to get anywhere with that. That leads us to the Kirchhoff's laws. That's kind of the answer for everything. If we could even, never do series or parallel stuff. It just makes it so much nicer that we like to learn about it and talk about it. But the Kirchhoff's ones will work, and so I'm just going to make a loop again. And so maybe
this is my big question was, do you do a loop with the live battery and the dead battery, and then a loop with the resistor and the live battery? That's what I'm thinking about doing.
I would say that, okay, the same thing I said in the last section, do the small loops. So the first loop would be on my left, which would involve the live battery and the dead battery.
Oh, okay.
A,
And then
B,
the dead
C,
battery and the resistor.
and then the dead battery and the starter. That now, the truth be told, there is a big overall loop. The real key, though, mathematically, is those three loops will give you three equations, but only two of them are independent. So you could do whichever two of the three you want. So you don't have to do the small ones. You could do the left loop and the big one, or you could do the right one and the big one. I just find it easier to think about and explain to do the small ones.
Right.
Because anything bigger than a small one is a linear combination of the other ones, and it's not independent. So you're not going to get a new equation. Yeah, so I think you hit it there, that if I do the loop A, B, C, D, and I add up all the voltages around a complete loop, I'm going to get 0. So from A to B, I would go an increase of 12, little bar to big bar. Then I would have what I've called current 1 and a resistance of 0.01. That's Ohm's law. And I've got a pause and say is a positive or a negative, and I'm going with the current, so that's a negative. Then I go B to C, nothing, no voltage change there. Then I go from C to D. First thing is a resistor here. So this is a current of I2 and a resistance of 1. And I would be going against the current, so it'd be a plus. And then right here through the dead battery, I'd go from big to little. So that's a negative and 10 volts. And then to finish up, D to A, there's no change. That completes the loop. That equals to 0. Maybe simplifying this a little bit, this would be 0.01 I1. And I move it over. This would be negative I2. And then this would be equal to 2 once I put the 12 and the 10 together. So I would call that equation number 1. The other loop, and if I just do the D to C to E to F back to D, and maybe I should have said back to A here. That's the right loop. That's kind of what you were asking about. And I said, yeah, do whatever loop you want. Got to do a second loop. So here I would go D to, and then of course I would do this battery. So little to big, that would be a plus 10. Then it would be current I2 times 1, and I'm going with the current, so it would be a minus. Then C to E, no change. E to F would be a current of I3 and a resistance of 0.06. I'm going with the current, so it would be a minus. And then finally F back to D, completes it. And that would be my second loop. Maybe simplifying it a little bit, I would have I2, when I bring that over, it's a plus, another plus for the 0.06 I3 equals 10, and I'll call that number 2. And of course, you want to pause for a moment. You'll see that these two equations together have 3 unknowns, so we need more. And of course, we need just one more. So that's where we're going to do the node rule. It says the sum of all the currents coming into a node equals what's going out. If we look at node C here, it looks like I've got it labeled so that 1 is coming in and 2 is coming in and 3 is going out. So 1 plus 2 equals 3. And so there's my 3 equations, 3 unknowns.
Okay, and you can just solve this with the matrices.
Yeah, good. And so like I showed you the other one, I'm going to set up a 3x4 matrix and punch it out.
Okay.
And just for completeness, since we already went through setting it up, I'll do this a little quicker, but But I'm just curious to see which way that current number 2 is, and then how big these currents are. They tend to be pretty big in cars. I don't know if these numbers they gave us are realistic. They may or may not be. They seem like they might be. So I'm just going to kind of quickly then edit my matrix A and call it a 3x4, and go with my first, and this would be 0.01, enter, -1, enter, 0 current for number 3, and that has to equal to a 2. My next equation would be 0 for current number 1, 1 for current number 2, 0.06 for current number 3, and that would have to equal to 10. And then this last one would be a 1 and a 1 and a -1. Okay, and then a 0. And maybe I'll just kind of scan it all. So I should go 2, 10, and 0, good. And for current number 3 should be 0.06 and -1, good. For current number 2 up here, it should be a -1, a 1, and a 1 finally. And current number 1 should be 0.01, a 0, and a 1. Nice. All right, so I've got my matrix set up. So now all I have to do is go to matrix and select my math, go down to the RREF, go to my matrix, select matrix A, hit enter, and it'll go through all this. And it looks like I get for current number 1, 170, let's call it 72 amps. Oh, current number 2, that's what I was curious about, it's negative. So this battery was low enough that the first battery
Is charging it. Right?
is actually still in the process of charging it while it's still trying to start this starter motor. So maybe here I should have put 171.7, because then what's going through the starter motor is 171.4. So a little bit has come off of the good battery and is charging the battery, not by much. But it does, the dead battery is kind of hurting our ability to start the car here. It's not even helping it. Which, as a practical sense, it's why you can do one more thing. A lot of times when you first hook this up, you go to start the car or do the jump start, it doesn't work. And if you leave it on there for a few minutes, and so maybe you leave it there for 5 minutes and try again, or maybe 10 minutes and try again, this could build up enough charge onto this one that it can now either contribute or it's not draining as much, and so the car starts while it's jumped. But sometimes what I'll do is then rev the engine, and that would be like adding more current, not just from the battery, but from the alternator. And so that will take care of the little, fact that this is draining some. And so now my good car is getting a lot of current, not just from the good battery, but the fact that the good car is actually started and the engine's revving, and be like another power supply. So I don't have to wait the 5 or 10 minutes, but
Yeah.
anyway. So, good problem.
All right. Thanks.
You bet. Yeah, good practical stuff in these chapters. That's why I said our first 3 chapters were a lot of science and physics and what's the fundamental ideas, and these next 3 chapters, the capacitors and then the Ohm's law. Now this one are a bunch of good circuit ones on actually putting this to use. Hopefully, being able to take it from the textbook to the real world. Jump starting is a good one, and designing it. So, and a side note that's about to change. We're going to next week, we're going to enter into magnetism. So we're going to step away from our electronics for a while and kind of learn some basic physics of magnetism. Then we'll get into a couple of chapters on applying our magnetism.
Magnetism. Is this just as hard as electric fields?
I'm going to answer this way. I'll put it in the same level, but here's why. The part that makes it easier is all these techniques and thinking strategies that we're learning right now, we're going to do again for our magnetism. So you can take what you've learned in these first 7 weeks and extend that to magnetism. So you don't have to relearn those. So that's the real good news. That in that sense, it makes it easier. However, magnetism is, by its nature, just harder than electricity. It's just harder, and so those two kind of balance themselves out. So magnetism, you can't do any magnetism until you start thinking in 3 dimensions. So I mean, we've had plenty of that in our electricity, so that's not too new, but at least we can do some of our electricity in 2 dimensions and draw them on a piece of paper. Everything's 3-dimensional. So, but then, like our flux and stuff for electricity and Gauss's law, that was very 3-dimensional too. So this whole class is very 3-dimensional, but magnetism is even more so 3-dimensional. And that's why we'll have these little techniques I'll teach you about, try to figure out where things are going, and we'll do our right hand, and we'll do little movements with our right hand like this and like this, and we'll just kind of adjust our right hand to kind of figure things out. But very 3-dimensional. So
Right.
Hopefully that was a good answer that didn't scare you too much. Because then the last part of the semester, we try to do situations that are really important to modern technology, but they're the 2 of them going on at the same time. So you have not only electricity, but you also have magnetism at the same time. Just by that nature, it's doubly hard because you got to worry about both of them at the same time. And they feed off each other. So, but it feeds off in a great way. I mean, we couldn't have modern society and modern technology without it. So that's why. In terms of nature, we're lucky we have it. In terms of learning, I wish nature wasn't so complex.
Yeah.
All right. Hey, Daniel here. He says, you have a generic question for me. All right, fire away.
Yeah, so I'm working on problem 13, but I thought I was doing it right, and then I looked at the solution, and why is it 1/1? It's 1/1 to the 9 plus 10. Like, why wouldn't it just be the and I ran into this problem on an earlier problem.
I'm gonna have to look that one up. It doesn't sound familiar to me. So let's see. Back to the textbook, and number 13. I think I heard you say.
Yeah, number 13. So I was just doing the
the switch one. Yeah. This is a good one. Okay.
And the way I was looking at it is that first 90 and 10, that's in series, so you can just add those normally.
Well, okay, wait. It depends if the switch is open or closed. So I assume you're talking about open?
Yeah. Oh, I see. So if it was closed, then
If it's closed, then here, let me draw a little picture.
Do the whole problem and just.
Yeah, maybe since I got it on video here, and somebody else might have the same question later on this weekend. But chapter 28, number 13, is actually a very common design in electrical engineering, because that closing of the switch is a dramatic change in the overall resistance. And of course, then the computer could pick that up and then know what something happened. Okay.
Mm,
So it would look like this. And maybe I better just read it here. It says, when the switch S in the circuit is closed, will the equivalent resistance between point A or B increase or decrease? State your reasoning. Assume that the equivalent resistor changes by a factor of 2. Determine the value of R. All right. Now, when things are in parallel, they tend to be lower resistor than in series. So with some experience, you would be able to say in the open position, there's a lot of resistance, and in the closed position, there's a little bit of resistance. But I'm not even going to go there. I'm just going to work out the math here. So I'm going to do this. I'm going to say, let's look when the switch is open. And that's the picture that they have. And so it would look something like this. You would have this unknown resistor R that would then branch out where there is a 90 and a 10. And then because the switch is open, I won't even draw the switch in my circuit diagram. I'll just do that. And with the switch open then, this 90 and 10 in this first branch would be in series. So these would be equivalent to 100, and the other branch would also be equivalent to 100. Now, when you two have two 100s in parallel, that comes out to be 50. I'll show you here. If I go 1 over 100 plus 1 over 100 equals 1 over the equivalence. 100 plus 100 is, of course, 2 100s, which is 1/50th. So this is saying that with the switches in the open position, these four, the 90, the 10, and the 90, are equivalent to 50. So in the open position, you have an R with a 50. And so the overall equivalent resistance, we'll go R total, would be this R plus this 50. So let me call that page 1. So again, that's what I would get when it is in the open position. Now,
okay.
let's try the closed.
In the solution,
Yeah.
just for the open one, why did they do 1 over? It's like it's an extra step for rather than just 1 over 50 and take the reciprocal of that.
Okay, so in the solutions, they did this. They kind of did my individual steps as one big step. They did this. They said, let's take the 90 and the 10 and add them together to get the equivalents. Then they said, let's add these two together, the 10 and the 90, to get the equivalent of those two. So that's where I got the 100. Then they said these two are in parallel with each other. So if I take their results, I would get this equivalent. And they didn't actually do a number. What they then said is if you took the reciprocal, you would get the equivalent. So that'd be 1 over 1 plus 90 plus 10 plus 1 over 10 plus 90. And then in their last step, they said, okay, well, then that just is added to the R. So it would be R plus this garbage. So 1 over 1 plus 90 plus 10 plus 1 over 90 plus 10.
Okay,
And then finally
Yeah.
they worked it out and got 50. So they got R plus 50.
Okay. Yeah, the author who wrote the solution wrote that in another solution, and I was very confused because I did it the way you did it in another problem and got the same thing. So, okay, that makes a lot more sense.
Yeah, and I hope you see it. We're doing the same thing.
Yeah,
I just did it kind of in smaller piecemeal steps, so it didn't look so overwhelming. You just kind of put them all together, and it looks like, whoa, where'd all that come from?
yeah, I was wondering how they got the fraction on the bottom, but yeah.
Yeah, I see
Okay.
this a lot in solutions. It's too bad. I know. I think what happens, to be honest, is the author or the book, probably the book publishing company, hires graduate students to work out the solutions, and they know how to do the problems. I'm not sure they have the experience on how to explain it well, so they just say, "Oh, well, this is the answer." So the answers are usually right. Sometimes the explanations are not as clean as you would hope. And then this is an example of it.
Yeah, I like the way you did it better. Makes more sense.
Good. Yeah. All right. So, okay. So if you see those are the same, let's move on to the second half of this, which is what if it is now closed? And maybe just give me a new starting point, so I can keep referring back to the circuit. The circuit, when it's closed now, would look like this. Go back to my drawing. That, I believe, is an A, and then we would have this value R. That this is going to be the job of this electrical engineer. They want to put in a switch such a way that when the switch is closed, that the resistance changes. I think I said by a factor of 2. I better go back and read that question. But now, if somebody closes the switch, let's say this is a little push button on your dashboard. You push in that button, and now the switch is closed. And so this 90 and this 10 are connected across the middle. And that's going to change the overall resistance and the overall current. And the design criteria is to get it to change by a factor of 2 to 1, so that 2 to 1 is probably enough that the computer could recognize, hey, somebody pushed the switch. The current is now doubled. It was, let's just say 1 amp, and now it went up to 2 amps. So somebody must have pushed the button. All right, so I'm going to do the same thing, but here's where it differs. Back here, this 90 and this 10 were in series, so I put them in series first. Then the two collectively were in parallel. But what I'm going to have here, once I've connected them, is the 90 and this 10, not this one, are in parallel.
Okay.
So this is going to look like this. I'm going to get an equivalent of this 90 and this 10. And by symmetry, if you will, this lower one will also have a 90 and a 10 that's in parallel. And it, of course, will come out to be the same amount. And then the result of that and that would be in series. So I'm going to find out what that equivalent of just these two is. So I'll go 1 over the equivalent is 1 over 10 plus 1 over 90. So I'm grabbing my calculator. 10 reciprocal plus 90 reciprocal, enter, and the reciprocal of that is about 9 ohms. So this is a 9 and this is a 9. And since those are in series, I'll add them to an 18. Okay, so This R then is in series with the 18. So this would be R plus 18 would now equal the total when the switch is closed.
Okay. Cool.
Yeah. And did I read right? They wanted it to change by a factor of 2. So just looking at the circuit, I mean, what I have, you'll see that the opened one is always going to be bigger than the closed one. And that was kind of what I said at the beginning of this, that generally things in parallel tend to lower the resistance. It would be like having, 3 lanes on a freeway versus 2 lanes. It's just easier for cars to flow through if you got 3 lanes versus 2 lanes, or 2 lanes versus 1 lane. So the more things you have in parallel, the easier it is to flow. And then in this case, then, we want this R plus 50, when the switch is open, to be twice that of the R plus 18. And so this would be 2R plus 36 is equal to R plus 50. And so if I bring the 36 over here and subtract, what's that, a 14 and an R? Yeah, so if R is 14, this would be a 32, and this would be a 64. Now, and so 32 doubled is 64. And so hooked this way with a switch, so using a 10 and a 90 and a switch and a resistance of 14, I can develop a circuit that would double the current as the operator of the button pushed it in.
Okay. So when the switch is open, the voltage is decreasing.
Well, wait a minute. Nowhere in the circuit did we even say what the voltage was that we're hooking this up to.
I mean,
So I guess in summary, if the switch is open from A to B, there would be the equivalence of 64 ohms.
okay.
And then when somebody pushes the button in, then the resistance changes to 32.
Okay, so
And I might have confused you, because if I had hooked this up, let's say this was, I used the dashboard on a car. So let's say this was actually hooked to 12 volts. When the switch was open, I would have 12 divided by 64, and there would be 0.1875 amps flowing through. But when somebody pushes the switch, I would now have 12 divided by 32. That should double the current, and I'd have 0.375 amps flowing through. But the voltage would still be 12, and I was concerned when you were talking about the voltage change, and there was no voltage change here.
yeah, I meant the resistance.
Okay.
Yeah.
Yeah.
Okay, that makes sense. Cool. Thank you.
And actually, for whatever reason, maybe because we're talking about cars, I mean, this totally reminds me of that little light switch on the top of my dashboard. During the daytime, it gets a lot of lights hitting it, probably makes a low resistance or closes the switch so that there's a lot of current, and the lights on my dashboard are actually pretty bright. Probably, and then I want them that way because I want to be able to see them in the daylight.
Mhm.
But then when nighttime comes along, if they stayed that bright, it would be just too much light in my face as I tried to drive down a dark road. So that little detector up on top of the dashboard doesn't get the light, and that kind of opens the switch, making more resistance. And then the current going to light up my dashboard goes down, and the intensity of the light goes down. And then, of course, then at night I have a lower intensity, which again is what I want. And then I could even put over here on the side, I know my car has this little adjustable resistor. I could even turn down the current more and more, so the lights get dimmer and dimmer, and so the lights on my dash can be adjustable depending if I'm on a dark country road. I'll turn down the lights really low. Otherwise, I got too much light in my face and I lose my night vision out on the road. And then in the city, I change it so that it's as bright as it gets at night, so that I can see my dash.
Sorry to interrupt you. But do those daylight sensors, like, how do they decide when it's like time to give more voltage or like give more power or less power?
Oh, well, no. Okay, let's go back to our original circuit. They're not necessarily giving more voltage. They're the switch in here. So if I come back to the original circuit right here, and I put a photoresistor right here, okay? Now, what a photoresistor is when light hits it, it actually becomes a pretty good conductor. So during daylight, this would be a conductor. This would be the equivalent, and I should be careful. I'm not completely sure if those are photoresistors or not, and I'm sure every car manufacturer has its own features. But this is the thing that comes to my mind is photoresistors, or phototransistors, because you can set them up when the light is hitting them. They're actually a good conductor, and it would be the same as this circuit, which we did with the closed switch, which would result in a resistance of 32, which for the 12-volt battery would result in quite a bit of current, and therefore the light on my dash would be kind of bright.
Okay, so that's...
Then all of a sudden it goes away. So if this goes away, if I don't have the sunlight hitting it, this is now a very high resistor. This would be the equivalent of opening the circuit. And then I have a lot of resistance, and it would be like this. And now the current to my dash goes down. And of course, now my lights aren't as bright.
So the photoresistors can basically just trigger a switch or to either open or close, like those like little garden lights that have no light in them during the day, but then as soon as it like goes down and switch on, that's just because the photoresistors making the switch turn, right?
Yeah, that's a good way of looking at it, except I think you got this. I just want to make it clear. It's not a mechanical switch. There's nothing mechanical moving. It's just changing the resistance of it. And so when in a mechanical switch, when you close it, you have small resistance. When you open it, you have big resistance. These photoresistors aren't quite as extreme, but they can be pretty close. So when sunlight is hitting it, or any light, they have a low resistance. And when no light is hitting it, they have a high resistance. And so that would be the equivalent of turning a switch on and off. And of course, you don't have to mechanically do it. You can just, the sunlight would do it. And actually, now that you bring it up, I have one on my front porch like that. It's kind of nice. I just have the switch in the house on all the time. And then they have it wired in such a way that when the sun goes off or the sun goes down, that makes a low resistance. So it's kind of the reverse of what we're talking about. So you'd have to have a little more circuitry here. But it would go low resistance, and then that drives the power to my light bulb. And the light goes on. But during the daytime, the resistance is high. And so even though I have the switch on, there's just a small amount of charge going through that light bulb. And it doesn't turn on the light bulb. But it's a little bit. So it's not quite as good as if I turn the switch off. But this way I don't have to mess with the light. It goes on automatically when it gets dark, and it turns off automatically when the sun comes up.
Cool.
Yeah, and now that I think about it, the one on the dash of my car, it's got to be quite a bit more sophisticated. It's probably tied into the computer, which then ties into a software setting, because it probably just goes right to the microprocessor, and the microprocessor says light or no light, because I know mine's calibrated that if I go under, say, an overpass, so if I go under, the 101 freeway there, even though it gets dark, and the photo nothing happens for about 30 seconds, so there's something, the computer knows it went dark, but it's programmed so that unless it goes dark for more than 30 seconds, don't actually change it on your dash or your running lights. Because I see it really well when I go in a long tunnel. If I go into the tunnel, it gets dark, and nothing happens till I'm about 30 seconds into the dark tunnel. Then finally, when I get in the dark tunnel, I can see the headlights change from running lights to the nighttime lights, and then of course my dash changes too.
Yeah, I drive like an older truck, and I've noticed, and I put like an aftermarket radio in,
Okay.
so I didn't notice this with the stock radio, but when I turn on my headlights, I don't think I have like an automatic one like you have, but when I turn on my headlights, I look over at my radio screen, and if I'm using the GPS, it goes from the daylight mode, which is like white land and a blue path, to like nighttime mode, which is like black land and like a purple path, even if I turn it on like in the middle of day. So
so it must have some kind of, wait, say it again. There must be some kind of photo sensor to tell it night and day.
Yeah, so I think instead of like on my truck, instead of an automatic photo sensor like you have, I think my truck just has a manual photo sensor when I turn my headlights on.
I got you now. It reads your headlights. Yeah, it's taking the input from you.
Because
yeah. Oh, that's pretty clever though. That it's better than. Yeah, that is pretty clever.
Yeah.
Yeah.
I've always found these things interesting.
Because there was a time where you didn't turn on your headlights in the day. And you only turned them on at night. And the logic there is, well, if you're turning on your headlights, it must be dark. So therefore, I'm going to turn down the brightness on this screen. Otherwise, I'm going to blind you.
Mm-hmm.
But now there's so many places. I don't think you can get a car anymore. Because I think all new cars are required to have daylight running lights on.
Yeah, that's why I like the older cars, because they're easier to work on, less electronics.
Oh yeah. My father-in-law has a old 54 Chevy, and it's so interesting. For example, the heater.
Mm-hmm.
It's all mechanical. It literally is. You reach down and you pull a lever and you allow air to blow over the engine, and you control how much hot air you let blow in by just opening a flap.
That's cool.
And it has a little knob for cold start, and it truly is just a mechanical choke. You just pull it back and forth, and if you follow it, it's a cable going through the firewall I'm not even sure there's a firewall, but it goes into the engine compartment, and it's just a mechanical butterfly right on the carburetor. And not a thing is electrical. I mean, it's so easy to repair. The window, it literally is a crank with a gear, and the window just goes down.
Yeah. Now
It
it's
is-
like you can't even fix a car without
It-
plugging in a computer to it.
Yeah, it is. It is really, like I said, there is a few electrical, and I mean, it does have headlights, of course, and it does have a starter motor, and it has, of course, an ignition system. But I think that's about it.
But with those, you could just do a diagnosis with like a voltmeter or ohm meter,
Right,
and
right.
you're good. Whereas
Right.
now,
All you need is an ohm meter and a voltmeter. You can fix everything on that car. Now I'm trying to remember. I think that might even be the car that the windshield wipers are mechanical. You reach over and you grab a knob and you just go swipe, and then I guess you just unless you keep doing it while you're driving, you just let the rain build up again and then go swipe, and it's got a little handle.
huh? I don't think I've. Yeah, I don't think I've ever seen that on an old car.
Yeah.
At least not one in good condition.
Yeah, that's what I'm trying to remember because 54 doesn't sound old enough for that. They did a lot of that pre-World War II,
Yeah,
but
which
not
I
after
haven't
World War II.
worked on anything
So,
before World War II. Everything I've worked on has been after World War II. So
yeah. And in fact, that's what gave Jeep Jeep's got an interesting history because Jeep, during World War II, they were looking for this all-terrain, rugged vehicle. They were asking all the major manufacturers to build them something, and these guys in the garage of their own place just came up with this incredible machine. It is, the windshield wipers were all mechanical. The glass can fold down if you need be, if it's blasted out. They came up with a 4-wheel drive. They put the gas tank under the seat to save room. They put the wheel spacing close together so you can deal with ruts. And they took it to the Army, and the Army was just like, no way. This is incredible. And then because it was wartime, they said, we want millions of these, but you don't have the capacity to manufacture it. So we're going to give the contract to General Motors and build them. They still made their fortune, but they weren't completely robbed, but they just didn't have the capacity to put it out. Well, then of course, and then that's all the GIs when they came home, they said, I want a Jeep. And so all of a sudden Jeep became like the vehicle.
mm.
Yeah, it was almost as good in all-terrain as a tractor.
Yeah, I have a Jeep actually right under me right now.
Oh, really?
I'm right above the garage.
Ah,
Yeah.
okay.
My family
Now,
has
is that a newer Jeep?
it is a new, but it has a manual transmission, so it's cool.
Ah, okay. Yeah. Well, and Jeep always does a great job because they still build everything that I think. I don't think you can get a Jeep that's not 4-wheel drive.
Yeah, no. I don't think you can. Not
The
Or
yeah,
even
not
has
well, not
Clarence.
Wranglers, but the newer
yeah.
Cherokees you can get 2-wheel drive,
Hmm.
which doesn't make sense to me because Jeep is known for 4-wheel drive vehicles. So
Yeah.
Yeah, because the world changes. They probably, of course, are after that market. Because if you wanted to just haul the kids around, you only need a 2-wheel drive if you don't live in the snow or the ice,
yeah,
and you want a Jeep, but hey, I'm not going to pay an extra couple $1,000 for this all-terrain.
Yeah.
yeah.
So
I guess
I could see how it would change, but yeah, but
Yeah, but the Wrangler that I have, the systems in that car they're very strong.
yeah,
Like,
yeah. So
yeah.
yeah,
and I mean, there's nothing. There's not a lot of electronics in there either. Like the most advanced thing that's in like that car is the seat warmers.
Hmm.
There's no infotainment. It's just the radio. There's all the
Okay.
even though it's a relatively new car, it's all the older things, and I mean nothing's really breaking apart from the clutch pedal. But
Yeah, that's how my truck is. It's like a 2004 Ford Ranger, and it's at like 224,000 miles and still running fine because it's mostly mechanical, very few electrical components in it.
yeah, no, certainly, yeah. I mean the engine is just. I mean it's like it's brand new in the car. I think the transmission is a little rough because me and my brother learned how to drive manual on it. We probably messed it up a little bit.
Right. Right. Oh, good. Oh, hey, well, it looks like it's time for a little break here. So let's see, it's 2:00. Let's
See you
take a
back
little
in
break
an
and we'll
hour.
see you at 3.
Yeah, see you in an hour.
All right, bye.
Bye now.